Okay, this is the second installment on one-way ANOVA. Really kind of the third. We introduced it in the first lecture, but now we're getting into some last few specifics on this test. These are the learning objectives. We'll talk about multiple comparisons, performing multiple comparisons after completing a one-way ANOVA test, identifying which procedure to use, Fisher's LSD or Bonferroni Correction, and you should be able to manually compute a t-statistic for Fisher's LSD protected t-test, and compute an adjusted p-value for Bonferroni Correction, and then we'll get into APA formatting of results. So multiple comparisons. What is the point? Once you've determined that your null hypothesis is false, that it's not true that all the means are equal, you need to determine where the differences actually are, or maybe there's just one that's different from one other one. So you're going to do some pairwise comparisons. And you have multiple means, right? If you only had two, then you just do a t-test. So you've got at least three. And there are there's several combinations of pairwise comparisons that you could make, which you'll see later on. And there's a certain number of possible comparisons you could make. Not all of those may make sense experimentally, and I'll touch on that briefly later on. So the point of these procedures is, remember that performing multiple tests increases the probability of a type 1 error. Each test that you perform, each t-test with an alpha of 0.05, there's a 5% chance that you're going to reject a true null hypothesis. So you need a way to correct for that. Remember this example from this comic. So here are the two procedures, Fisher's LSD protected t-test and Bonferroni correction. This is kind of these are your criteria for, well, first, to decide which one. If you're making three comparisons, then you can use the protected t-test. Now, you may have more than three means that you're comparing, but there might only be three comparisons that are meaningful to you. Bonferroni correction is when you're doing three or more. And this is just kind of a rule of thumb that we're using for this course. There may be reasons why you may adjust this rule depending on your experimental question. For example, if you're anyway, there are reasons for using Bonferroni, which is a more stringent test. But at least for this course, use this as your rule of thumb. If you have three comparisons, then it's okay to use the LSD protected t-test. There's not a whole lot of correction that it does for the inflation of your alpha, and so it's not recommended if you're doing a lot of comparisons. One thing that does help to control for the type 1 error rate is that your F statistic needs to be significant. Okay, so you need to have a significant F statistic, a p-value less than 0.05 for that F. For this, you're going to need to calculate a critical t-value, and then you're going to need to compute the Fisher's LSD protected t statistic, compare that to your critical t-value for all comparisons. We do this, you're kind of limited by Excel because it's not going to give you p-values for these. Other softwares would be able to, so you could report exact p-values, but in this case, we're just going to be comparing the t-statistics that result from the LSD test to a critical t-value. Bonferroni correction is different. You are adjusting your alpha level to keep your type 1 error rate still at 0.05, but adjusting your cutoff, your threshold for significance to something lower, more stringent. This doesn't, in fact, require your F statistic to be significant, and I don't understand all the math behind this, but you can have a significant or a non-significant F statistic and still get some significant pairwise comparisons that show up after that. Probably just because differences in power related to each test. So what you'll first do is, well, you run your ANOVA. Usually the omnibus test, it's expected that you're going to report that in your results, even if it doesn't show up as significant. And if it's not significant, you should still report that, even if you are justified in doing multiple comparisons afterwards. You're going to divide alpha by the number of comparisons. So if there are 4 comparisons of interest, then you divide alpha by 4. And then you're going to do multiple 2-sample t-tests on each pair, each relevant pair, comparing each relevant mean to each other. So that's something that you've done before. You're just going to do it multiple times. And the only difference is if you get a p-value, you're going to need to compare it to your adjusted alpha, the new alpha, the Bonferroni corrected alpha, rather than the original alpha of 0.05. So Fisher's LSD protected t-test. Unfortunately, there's not a fancy formula in Excel to just compute this for you, so you'll need to compute it manually. But this formula is fairly straightforward. You have the 2 sample means that you want to compare. You divide that by the square root of all this stuff. The MS error, which you get from the ANOVA output, times 1 over sample size for the first one, plus 1 over the sample size for the other one. Okay, so see the other video on the demonstration of how to do that. But yeah, it just requires some manual calculation. So then this t statistic that results, you're going to compare to the critical t value. So you'll need to get a t. If this t exceeds, the absolute value of this t exceeds that critical t value, then you can declare that pair to be significantly different. Yeah. Bonferroni correction. Here's an example in which you're comparing 5 different means, and let's say that let's look at just all the possible comparisons that can be made. I think it's helpful to make a little table like this in your Excel workbook just to make sure you've got all of these possible ones covered. So with 5 different groups, you can do group 1 versus 2, 1 versus 3, 1 versus 4, 1 versus 5. And now we can blank out this row here because we've already got 1 versus 2 right here, 1 versus 3, etc. You can do that with these other rows. And you're also just blanking out this diagonal because you're not going to be comparing group 5 with group 5, group 4 with group 4. That doesn't make sense. Okay, so you've got 10 possible comparisons left. Now, even not all of these may be meaningful, so you may still not want to do all 10 in this case. For example, maybe you are group 1 is your control group, and then you've got these 4 different treatments, and you just want to see which of if any of these treatments are significantly different from the control. You're not going to want to compare, you may not want to compare all the treatments with each other. You just want to know if they're different from the control group. Okay, so you would only do these 4 comparisons in this case. If these were all relevant to you experimentally, then you would divide your 0.05, your alpha of 0.05 by 10 to get 0.005. Okay, so when you do these 10 t-tests, it gets a little tedious, I know. You run these 10 t-tests, and you'd only consider results with a p less than 0.005 to be significant. Okay, and just make sure you decide beforehand what this number actually needs to be. You've got all the possible comparisons that you can make. How many of those are actually scientifically relevant, and only divide by that number. Okay. There are other procedures as well. There's like the Tukey's test. There's like a chef's test or something. We won't cover those in this course. And which one you use, I mean, we have kind of this rule of thumb of 3 versus greater than 3, but it may really depend on your experimental procedure and your research question. Bonferroni, as I mentioned, is quite a stringent method. There are some that are a little bit more lenient. And you might be okay to use Fisher's LSD test, for example, for more than 3 means if you are just kind of doing some exploratory analyses. Like a good example is screening drugs. You're just screening a drug across all these different cell types or whatever, or seeing if it reacts with all these different biological chemicals, and you want to know where is there some kind of an effect that's worth exploring further, and then you get more stringent after that first step. But that's just kind of an initial first pass to see where is a good place to look. So type 1 error in that case may not be that bad of a deal. Some APA formatting stuff. I know this slide is very text heavy. These slides will be posted so you can refer to this while doing your assignment. Some things to remember about APA formatting. Active voice is preferred. It's perfectly acceptable to say I conducted a one-way ANOVA test instead of a one-way ANOVA test was conducted. Or if that's just one author, on your paper, which when you're doing this for the lab, it's just you. If you've got multiple authors, then you'd say we. Following this slide, there's some review of formatting of F&T statistics. So it is important, if you look at the manual, it is important to make sure that you are indicating which statistics are significant versus non-significant. Even if it's a non-significant result that doesn't really jive with your hypothesis or doesn't look very good, you still need to report it. You got to be transparent with all the analyses that you did. But based on examples that I saw, it's not always necessary to report all of the exact statistics. Like if you're doing 10 different t-tests, you probably don't need to list, post hoc comparison. Oh, and by the way, you'll see that phrase post hoc. That just means like after the fact. After doing this omnibus test, then you'll do some post hoc comparisons. If you're doing like 10 of those, then you probably don't need to report the exact statistics, the t value and the p value for all of those. You may be able to do something, it may make more sense to do something like this, where here are the exact statistics for the ones that were significant and all the other ones were non-significant. All t was less than 2.01, p greater than 0.008. Okay. Now, you should note that the APA wants you to include effect sizes, confidence intervals, things that aren't just saying, hey, this is significant or this isn't, and then getting reporting what the size of the effect is. We aren't covering that for this lab, but we will talk about it later on. So just know that's something that we'll be adding later, and we'll talk about some effect size measures for ANOVA. Okay, and then these are results in APA format. This looks pretty simple, but there's kind of a lot to keep track of here. Just make sure you're italicizing the F and the P. I think I forgot to mention that previously, but yeah, you do want to italicize the P. Make sure things are reported to the proper number of decimals. You've got spaces before and after the equal sign, after the comma. So this is what you want your F statistics to look like. And then your T statistics, similar format, italicized, degrees of freedom, to do 2 decimal places. Exact p-values without a 0 in front of the decimal. Unless it's less than 0.001, then you can use the less than sign. Okay? All right, that's all for this one.